So anyone who has gazed upon mountains during storms may have recognized or suspected that alpine topography actually influences the distribution and intensity of rainfall or precipitation within the mountains. Over the last 2 decades, geologists have been interested in the opposite idea, that climatically driven erosion may influence not only the topography but also the deformation within collisional mountain belts, a topic that I'll examine briefly today. By collisional mountain belts, I'm talking about belts that arise from the collision between 2 plates that comprise continental crust. And the Pyrenees, the Alps, the Appalachians are examples. And I'm going to talk today about the Himalayas, where the Indian plate has been colliding with Eurasia over the last 50 million years. And today, the shortening across here, the collision still occurs at a rate of about 4 centimeters per year. Now, unlike a lot of other sciences, we don't have time machines that allow us to run experiments back in time, but we gain some insights from things like analog models. These are sandbox models where we're pulling 2 masses of sand together, and we see the way it deforms by a series of faults and forms these sort of a 2-sided wedge that we see here. And these sorts of insights, along with numerical understandings of how rocks deform and geophysical and geological measurements, have underpinned the development of numerical models that are coupled with this deformation in the subsurface and erosion that occurs on the surface. And this movie here is one that's illustrating the topography of one of these 2-sided wedges. And what you see is that the surface is always changing, and yet it moves into a basic steady state overall, in which it's driven by the asymmetry of rock uplift in the bottom, and we end up with the drainage divide migrating to an equilibrium position where we have steep slopes on the right, gentle slopes on the left, more erosion on the right, less on the left. These are all designed, they all balance the rate of uplift by erosion, and we develop a steady state topography. Now, in these models, the rainfall that's driving the erosion is uniform across the model. And you might ask, what would happen if we had wind and rain coming in from the opposite sides of the mountain belt? And the models predict a really profound difference, or startling difference between these 2 end members. So here the rain and wind are coming from the left, down below they're coming from the right, and the area of maximum deformation, shown in bright red, are on opposite sides of the mountain belt. The pattern of erosion, which is shown in the gray mesh up here, is rather different. And you can imagine that this redistribution of masses within a mountain belt has a major impact on the stresses within it, and these, in turn, could modulate slip along fault. And in this case, the whole geometry of the mountain belt is predicted to change. Now, you could ask, okay, how do we test these? And I'm going to show you one example from the modern time that combines just these top 2 things. We're looking at deformation and climate here. We ultimately have to integrate all of these, but we'll look at deformation and climate in terms of seismology and geodesy, that is, with using GPS to measure movement within the Earth's crust, and a little bit of meteorology. And we're going to be looking at the effect of the Indian monsoon on seismicity within the Himalayas. Kind of interesting connection in real time. Every summer, the Indian monsoon sweeps up out of the Bay of Bengal and sort of explodes against the southern margin of the Himalayan topography. And it dumps 1 to 6 meters of rainfall in those 4 months of time each summer. And whether we use satellite altimetry or gravity measurements, we can see that the level of water in the basin out in front, called the Foreland Basin, has this very cyclic period. The blue arrows indicate the summer monsoon, and the water rises rapidly then and slowly drains away in the ensuing months after the monsoon ends in September. If we look at GPS measurements, continuous GPS measurements within the Himalayas, these are now measuring north-south contraction across the range. You see a cyclicity to this too, but it's exactly out of phase. When the monsoon loading is strong, the GPS contraction rates slow down, and vice versa. And if we look at seismicity within the Himalayas, looking at earthquakes greater than magnitude 3, we see a similar cyclicity to it, in phase with the GPS and out of phase with the monsoon. So this is a striking example of a direct connection, apparently, between these, and the conceptual model for why they are connected is shown here in the idea that the water loading that happens within that basin on the front of the Himalayas drives subsidence, and it causes a sort of stretching flexure of a plate. And in this part, in the northern end, and the southern end as well, but that ends up adding a component of extension within that part of the mountain belt. And that extension actually opposes the rate of shortening. There's about 17 millimeters a year on average of shortening across the Himalayas themselves. The extension that's generated by that load opposes that, so the seismicity goes down. And as the water drains away, that you actually get an extra component of shortening, so the seismicity goes up. So we have a very wonderful, explicit, direct connection between these phenomenon that we deduce within the Himalayas. Now, if we try to go back in time, there are immense challenges in trying to do these sorts of studies because the natural landscape is very noisy. Looking here at the Himalayas, we have glaciers and rivers and landslides. We have rocks that are weakly consolidated sediments to very resistant metamorphic rocks in the range. And so it's a very noisy environment, and it's a challenge to extract real meaning from that. But we tend to go to places where the rates of deformation are fast, which is why we go to the Himalayas, and so the signal can hopefully rise above the noise. And there are a number of new technologies which have come to aid us in the last couple decades. We now can look pretty much at the entire Earth at 30-meter resolution using digital topography. We are getting a better and better picture of global climate at high resolution so that we see climate at cells that are 5 kilometers on a side or so. We can start to combine those two data sets. So for example, in the front of the Himalayas, we have some places where we have one band of really high rainfall and other places where we have two bands. And if we look at the topography associated with those, we'll see that where we have steadily rising topography, as shown on the bottom left, we have one peak of rainfall up to 6 meters during the monsoon. And where we have step topography, as shown on the right, where there's an initial step and then a big step, we end up with these two peaks. So we're starting to understand what's controlling the rainfall patterns around mountain ranges. One of our big challenges is figuring out ways to inject time into landscapes and to be able to calibrate rates in the past. We always say, no dates, no rates. So here's an example of a river that's beveling laterally and creating this flat sort of surface that we call a strath. You can imagine what happens if this river then incises, it leaves that strath behind. So if we could figure out the age of the strath, measure the incision, we could come up with a rate for river incision. In the past, we never could have dated a bare bedrock surface, but now we have geochemical techniques which allow us to tell how long that surface has been exposed in that position. So we end up being able to deduce or calculate out what the incision rates are. So that's moving down into the surface. We also can watch rocks sort of come to the surface as they come up through the thermal field underneath the surface. So we look at them going from high temperatures to low temperatures through time, and we can get a general erosion rate of that surface approaching the rocks or the rocks approaching the surface, whichever way you want to look at it. So I'd like to look at one example from the northwest Himalayas. And this is an area where there's very high topography. Here's Nanga Parbat, one of the 14 highest mountains in the world, and the Indus River flows through here. There's a 7-kilometer difference in altitude between the Indus River here and the top of Nanga Parbat. So we might wonder, what are the variations in erosion rates across this landscape? And we've looked at that using these geochemical techniques to date erosion surfaces, strath surfaces like this, and these are a lot of the ages back to 50 or 70, 80,000 years ago, and their heights above the river. And from these, we can deduce river incision rates that range from less than 2 millimeters a year up to 7 to 10 millimeters a year. Those rates may not sound much, but when you translate them into geological times, they represent 7 to 10 kilometers of erosion in a million years, which is a lot of rock to get rid of. We might ask whether these rates that we measure at the sort of 10,000, 100,000 year time scale are persistent through time. And when we look at that, we use the cooling of the rocks below 120 degrees in this particular case, and you see a trend of ages from as young as 500,000 years to over 8 million years across the same span. And those can be translated with geothermal models into erosion rates as well. And you can see they mimic the erosion rates that we get with the Strath terrace data to suggest that this pattern has indeed been generally persistent over the last 500,000 to 1 million years at least. So how about the topography? How does it vary across this range in erosion rates? We might suspect that high rates would correlate with steeper topography, for example. So we use the digital topography across this more than 10-fold range in erosion rates, collect up all the hill slope data, and synthesize them, stack them all together, and here's a plot in which we're looking at the frequency of different hill slope measurements. So there's a probability density distribution, and all these different graphs stack right on top of each other. In fact, Nanga Parbat, probably the most rapidly eroding area in pink there, has a slightly gentler mean slope. So they're all about 35 degrees, independent of the erosion rate, it turns out. And you might wonder, why is that? Well, we can start to address that question by looking at these two sort of end-member landscapes. At the bottom is a soil-mantled, grass-covered landscape with gently sloping hill slopes. And above, you can see the very steep, rugged, planar, bedrock underlain topography of the Himalayas. And on the right, we see data that relates basin slope, the average basin slope, with erosion rates. And where rates are slow, up to 1 or 2 or 3 millimeters a year, there's a relatively planar relationship between the erosion rate and the slope of the basin. But once we get up to a couple millimeters or so, the erosion rates are pretty much independent of the slope. The slopes are close to 35 degrees or so, as we saw in the previous slides. Why is that? Well, as far as we know, from all the studies that have been done, the maximum rate of production, of conversion from rock to soil, is 0.3 millimeter a year. For any rate, if you're eroding faster than that, you have to involve bedrock, and basically the way we erode bedrock rapidly is through landslides. So in these high zones, we're going to be having bedrock landslides, and we expect these hill slopes to be near the angle of repose for their strength. Down at lower rates, we can have creep happening. When we look at the northwestern Himalaya, we see that all these rates are above 0.5 millimeter a year, so it's not surprising that, in fact, they are denuding by landslides and have very steep slopes where they all look the same across the spectrum. All right, so how do we measure the rates within this landscape? And why do we think that, for example, that we could use the incision rates of rivers to characterize the whole landscape? That's illustrated in this graph here, where we've taken a swath of the topography. Here's the swath where we're plotting maximum, minimum, and mean topography. across there, and what you can see as the slopes are incredibly planar and high. This is a 2-kilometer high slope. It's about 4 or 5 kilometers long, so they're high and steep. They're near 30 to 35 degrees, so they're poised near their threshold angle for failure. And we think that, therefore, we can actually use the river incision rates to characterize the entire landscape. And the reason for that is this. We think that the hill slopes are basically, because they're poised at a threshold, are more or less a slave to the rivers. As the rivers cut down, the hill slopes have to follow behind, like this. So that means when we measure these rates of river incision, as we did on the Indus, then we can characterize the rate of erosion through that entire landscape. And here are these examples of erosion at kilometers per millions of years that we find both with strath terraces at the 10,000 year scale and then with cooling ages at the million-year scale that help us to define how that landscape has been deforming, what the rates of erosion have been across it over the past perhaps million years or so. Well, there are lots of challenges left for us. We have very little insights about the way fault slip rates change and erosion rates change at climatic timescales. That is to say, the 10,000 to 40,000 year timescales that modulate major climate cycles within the Earth. We have a few techniques where we're trying to get at paleo-altitude in the past, but it's a very difficult problem to tackle. We have relatively little information about continental paleoclimates. Most of our paleoclimate information comes out of the oceans, where we have much more continuous records by and large. And we're still have a lot to understand how we're going to couple the deep Earth with the shallow Earth and the surface. But there are interesting challenges which we're continuing to address in the coming years. So thank you.